Hi, this is the third video in the probability functions section on the binomial distribution. Let's just do what are we talking about here? The binomial distribution is a discrete probability function, probably the key one, the most important and one in this level, with probably the most interesting and tricky questions. What does it do? It defines the probability of X successes in N trials where the probability of a success is P. So let's just think what that could mean. For instance, if we're throwing darts at a dartboard and we're trying to hit the ball, so a success would be hitting the ball. The probability of hitting the ball with any one dart would be whatever P is, 0.1 maybe, something like that. So if we have 20 throws, let's say the probability is 0.25 because that fits in with the diagram. If we have 20 throws, then would do is count up the number of the number of balls that we hit. Okay, and that number would be a random variable. Okay, so we're about to embark on this throw of 20 darts, and if we want to predict, knowing that with any one dart we've got a 0.25 chance of hitting the ball, we would conclude from this, therefore, that the probability of hitting the ball 7 times out of those 20 would be given by this, which looks like 0.11. That would be the chance of exactly 7. At least 7 will be the sum of all these. This one. These obviously very small anyway. That would be that. The probability of less than 3 would be the sum of this one, and this one. And so on. So a success is what this gives us. In some situations, the terminology for a success can be a little bit confusing because we might be talking about number of times that a test is failed, and in binomial speak, fail would be a success, because that's the thing that we're applying the probability of 0.25 or whatever to. Okay, so that is basically the idea. We do 20 trials, and as a result of that, there are 21 different outcomes from 0 to 20 inclusive. All right, so yeah, 20 trials. P equals 0.25. What's the probability of exactly 3 successes? Well, we would write probability that the random variable X is equal to 3. Now, this is calculated as 20C3. This is the coefficient that we've seen in the probability section. I won't go back over why we justify that, but just to say that the value of that is 20 factorial divided by 3 factorial times 17 factorial. That's 20 choose 3 times p to the power of 3. That's this. And then q is that we sometimes use q for 1 minus p. Is a little bit more concise, as long as we know what we're talking about. Q to the power of 17. So perhaps see where this is coming from. 3 successes, 17 fails. So that's how we would calculate that. However, we're seldom going to be doing that because we've got our calculator. And so just quickly to kind of go through the process that we would use here, if we go into menu 7, let's just do that again. It's menu 7. And then we are using the binomial probability distribution. There is also a cumulative which we would use if we're looking for what's the probability of at least 3 successes or more than 5 successes or something. But we're just looking at this binomial here. So choose option 4. List or variable. List gives us the option calculating lots of probabilities at the same time. Variable, there's the 2. So now in our binomial terms, x is 3. X is the value of the random variable that we're actually trying to calculate. So that will be 3 equal. N is the number of trials. So that's 20. And P is the probability of a single success, 0.25 equal. And equal again. So that's going to give us this probability, 0.134 for 3 decimal places, 0.134. So that's what that would be. Okay, so that is more or less how that works. We'll come back to the cumulative function in a minute. Okay, so this distribution, I think we talked about in previous video, does have an expectation. Think about being a mean as well, and a variance, a measure of its spread. We're looking at it. It's, you know, it is spread up. Spread. If there was no spread, it would all just be one single bar here, one single spike. But it is spread out. So the expectation of x would be the number of trials times this probability p. Now for this, it's we'll multiply it together, we're going to get 5. So that would be the expected value. That kind of fits in. We'd see this is actually the most likely value here. So that kind of sort of makes sense, doesn't it? It also has a variance. And interestingly, the variance is equal to n times p times q, which is 1 minus p. So if we know n and p, we therefore know both the expectation and the variance of the distribution. And then, of course, standard deviation that we use sometime, and we'll see this coming into play in later videos, is the square root of the variance. So that's quite neat. There is a bit of maths that you can use to actually demonstrate that the expectation of the random variable is NP. I'll not run through this. I'll leave it on screen if you want to replay the video and pause and just have a look at that. Then that would be possible. You don't need to be able to do this. But that would be just for interest if you wanted to do that. Okay, so that is sort of the bones of it. Let's have a look at a couple of examples. Okay, here we go. A drugs company claims that 75% of patients suffering from depression recover when treated with a new drug. Excellent. A random sample of 10 patients with depression is taken from the doctor's records. Write down a suitable distribution to model the number of patients in this sample who recover when treated with the new drug. Okay, so this is our P here, isn't it? At 0.75. We've got 10 patients, so we're doing effectively 10 trials. Okay, and the number of patients who recover, that will be your random variable, typically big X. Now we write down a suitable distribution. This is notation for binomial, and these are the parameters that we use with it. The first one is the number of trials, and the second one is the value of P, the probability. So that notation would be sufficient to answer that question. One thing that has come up, I've not put down on here, is that if we are using this as the in order to model this particular situation, there are a couple of things that need to be true for this to be our model, and we can remember this really by this these initials I D, and this basically means that each of these patients or each of the responses from the patients has to be independent, and they have to be identically distributed. So they have to follow the same probability distribution, but they have to be independent. So somebody, so give it to two people. If one is successful, it doesn't make any difference as to whether the other one is successful. So that's the little reminder, if you like, for the conditions for this to be a valid model. Okay, so given that the claim is correct, find the probability that the treatment will be successful for exactly 6 patients. Yeah, okay, so the probability that x equals x is this distribution, as we've said, and therefore the probability that x equals 6 is 10, choose 6, this, which equals that, but we're not going to, well, we don't need to rely on this calculation. We can actually do it, but of course that is basically the same as we've just done on the calculator. No point getting the calculator up. Menu 7 on the calculator, and we can work that out quite easily. So that's that question, and that's that's sort of fairly common sort of thing. Okay, let's have a look at this one. All right, so this is I think this will do us for the binomial at the moment. The probability of a bolt being faulty is 0.3. Now, here's where the terminology can be a little bit confusing. So we're sort of saying that 0.3 represents a success. So we're success if we found a faulty bolt. Yeah, okay, but that's binomial terminology for you. Find the probability that in a random sample of 20 bolts, there are exactly 2 faulty bolts. Okay, so we've got our P is 0.3, our N is 20. This is the binomial distribution. This is how we describe it. So the probability that the random variable is exactly equal to 2. Again, get the calculator out, and we'll work that out to 0.028. And then there are more than 3 faulty bolts. Right, now the way the calculator works is that it will actually give you, if you choose a cumulative binomial, the x corresponds to this x is less than or equal to 3. So let me just show you that. So we'll pull that over there. So menu 7. Right, we're going to go with the binomial cumulative. We're just going to go for single variable. It's 2. So here, so the probability that x is greater than 3 is equal to, well, 1 minus the opposite. So less than or equal to 3. So this is 0, 1, 2, or 3. This is 4, 5, 6, 7, and so on. So our x is 3 from there. Our n is 20. Oh, all right. The thing with this is if you hit equals 2 consecutive times, it bombs off into the answer. So 2, so we've got 3 equals 20 equals, and p equals 0.3, 0.3 equals 0.2. 107 to 3 decimal places. So that's 1 minus 0.107, giving us this answer here. Okay, so that's good. Part C, and this is a common thing in these questions. It's on this one, so I'll just flag it up. So if you buy, so now we've kind of changed the goalposts a little bit. Bolts are sold in bags of 20. John buys 10 bags. Find the probability that exactly 6 of these bags contain more than 3 faulty bolts. So we've changed the problem slightly. So we now, the probability of one of the bags having more than 3 faulty bolts is, as we just calculated, that we're buying 10 bags, so our N is 10. And we're interested in the probability that, let's just use another letter because it's effectively got a different random variable. Y is greater, sorry, exactly 6, Y equals 6. So, so if we were to get our calculator back up, menu 7, and we're going to use, well, we wanted exact, so the binomial probability would be good enough for us. So here we got an X of 6, an N of 10, and a P of 0.893. And that's going to give us this value here of 0.014. And as always, when you are rounding, always put your accuracy in 3 decimal places. Okay, so a couple of examples there as to how we use the binomial. At that level, it's actually quite straightforward, I think, really. All the work's done for us on the calculator. So what we have to do is identify P and N and X and plug the numbers in. But do watch out if you do have any problems like this. For this sort of, this is, you know, your bonus question here, where you're actually looking at a slightly different problem. And typically your success rate is actually something that's been calculated in the first part of the question. But anyway, hopefully that's the idea there is to give you the principle. We'll be working through a few more examples on other videos. So hopefully that's kind of established the principle. So hopefully that was good, and I will see you next time.